Lecture 25 covers Section 7.2.3 through 7.2.4. At the end of today's lecture, you should be able to identify zero-force members within a truss, and you should also be able to solve a system of equations describing the equilibrium equations of pins of trusses using symbolics within MATLAB. Lastly, you should be able to conduct a parametric study of forces within a truss structure using MATLAB. To begin, we will discuss zero-force members. There are two situations where we can easily identify zero-force members by inspection. The first situation is when we have two non-collinear members connected at a shared joint that does not experience any loading or reactionary forces. In the image below, we can see members AB and BC are non-collinear and share a joint B, as well as members GH and HN, which are non-collinear and share a joint H. At these joints, there are no reactionary forces as well as no applied loads. Thus, these members are zero-force members. We can prove that member AB and BC are zero-force members. What we will first do is we will use the method of sections and isolate members BC, AC, and AI. In doing such, we can cast our equilibrium equations. Specifically, we are going to sum the moments of force about point A and set the summation equal to 0. As we see, RAX, RAY, FAI, and FAC all have lines of action that intersect point A and thus do not contribute to the moment. The only internal reactionary force that does contribute to our moment is FBC. Thus, the sum of moments about point A tells us FBC times its moment arm, which was 4.5 meters, must equal 0. And the only way this expression is satisfied is if FBC is equal to 0. We can then proceed by summing our forces in the y direction and setting this equal to 0. In doing such, we will see the RAY plus the y component of FAC, which is resolved using a force triangle, is equal to 0, knowing RAY is equal to 1/2 of our applied load from symmetry. Carrying this information forward, we can isolate members AB, AC, and AI using the method of sections. In doing such, we can apply our equilibrium equations in the y direction. Specifically, we find RAY plus FAB plus the y component of FAC has to equal to 0. We already know RAY is equal to 20 kilonewtons, and FAC was minus 24.04 kilonewtons. In doing such, we can solve for FAB, which is equal to minus RAY minus the y component of FAC. Upon substituting inner values and solving for FAB, we find that FAB is equal to 0 kilonewtons. This corroborates our rule that member AB and BC are going to be zero-force members, for they are two non-collinear members connected at a shared joint that does not experience any loading or reactionary forces. We can also determine whether or not a member is a zero-force member by inspecting other members nearby. For instance, when three or more members are joined at a shared joint, for instance, member AE, EF, and EB are all connected at joint E, and two of the members are collinear, i.e. AE and EF, while the others are not, i.e. EB, and there are no reactionary or loading forces, then the other members, specifically EB, are classified as zero-force members. Looking at the truss below, and based upon this definition, we can see member EB and ID are zero-force members. And we can verify this by using the method of joints. Using the method of joints, we will focus on pin E, and we know each member's forces act inward on our pins. That is, we have FAE, FBE, and FFE all acting inward on the pin. If we apply the summation of forces in the y direction set this equal to 0, we see FBE is the only force acting in the y direction, and this must be equal to 0. Thus, member EB is a zero-force member. Now note, when we looked at the interior of the truss, pin G had an external load of 40 kilonewtons. We are going to see member CG is not a zero-force member. That is, if we apply our summation of forces in the y direction about point pin G and set this equal to 0, we see that FCG has to be equal to the negative of the applied load, or minus 40 kilonewtons. When analyzing a truss, the most robust method of analysis is the method of joints. The method of joints creates an independent system of equations, and these equations consider both applied and reactionary forces. This system of equations can be cast as a simultaneous system of equations, which is solvable using matrix inversion or symbolics. Solving a simultaneous system of equations using matrix inversion has many benefits. One of the benefits is it's much faster than symbolics, which enables us to conduct parametric studies efficiently. You can cast a symbolic system of equations into matrix form using MATLAB's equation to matrix command. However, we will proceed using symbolics for this example, for the ease of constructing our equilibrium equations outweighs its slow computational time. Let's consider the following Warren truss. We want to solve for the internal reactionary forces in the members using the symbolics toolbox in MATLAB with a theta of 53.13 degrees. Then we want to solve for the maximum compressive and tensile forces within the members for various values of theta, given theta is between 45 and 70 degrees. We want to plot these forces as a function of theta. To begin, we are going to construct a free body diagram of each pin, and we note that the forces acting on the pin act toward the pin. We will start by employing our equilibrium equations about pin A, and we will define our symbols as theta, RAX, RAY, RAB, and RAC. Equation 1 is the summation of forces in the x direction about pin A. Here we have RAX is equal to RAC plus the x component of RAB. Equation 2 is the summation of forces in the y direction about pin A. Here we have RAY is equal to the y component of RAB. Moving to pin B, we will define our symbols RBD and RBC. Equation 3 is a summation of the forces about the x direction about pin B. Here we have RBD plus the x component of RBC, which has to be equal to the x component of RAB. We will cast this as RBD plus the quantity RBC minus RAB times the cosine d of theta. Here we have to consider the y components of RAB and RAC. That is, we have the quantity RAB plus RBC times sine d theta, and this is equal to 0. Next, we will consider pin C. We will define our symbols RCD and RCE. Equation 5 is the summation of forces in the x direction about pin C. Here we have RAC acting the positive x direction, the x component of RBC acting the positive x direction, RCE acting the negative x direction, and the x component of RCD acting the negative x direction. Thus, we can cast RAC minus RCE plus the quantity RBC minus RCD times cosine d theta is equal to 0. Equation 6 is the summation of forces in the y direction about pin C. Here we have the y components of RBC and RCD acting in the same direction as our applied load, 40 kilonewtons. Thus, we'll cast our equation as a quantity RBC plus RCD times sine d theta plus 40,000 is equal to 0. Next, we will proceed to pin D. Here we'll define the symbol RDE. Equation 7 is the summation of forces in the x direction about pin D. Here we have RBD plus the x component of RCD less the x component of RDE is equal to 0. Equation 8 is the summation of forces in the y direction about pin D. Here we have the y components of RCD and RDE equaling 0. Lastly, we will apply our equilibrium equations about pin E. We will define symbols REY. Equation 9 is the summation of forces in the x direction about pin C. Here we have RCE plus the x component of RDE being equal to 0. Equation 10 is the summation of forces in the y direction about pin E. Here we have the y component of RDE counteracting our reactionary force REY. With these equations and variables defined, we can make an equations vector and a variables vector, and then we can construct a solution structure by solving our equations for our variables. In doing such, we can print out each of our forces. We will note a positive value indicates compression, and a negative value indicates tension. In doing this, we find RAX is equal to 0 kilonewtons, RAY and REY are both equal to 20 kilonewtons, 1/2 of our applied load, and the members in tension are RAB and RDE, which is our outside diagonals, and RBD, which is our top beam. We see the greatest compressive force exists in our top beam. RAC and RCE have the lowest values of tension at 15 kilonewtons, and RBC and RCD have the highest values of tension at 25 kilonewtons. The last thing we'll do is check our global equilibrium equations from our global free body diagram. The first logical statement is to check if R, reactionary force in x direction, does not equal to 0. If it does not equal 0, an error will print. Our next logical statement is to see if our reactionary forces in our y direction do not equal 0. If they do not equal 0, an error will be printed. Lastly, we will check to see if our moment equation about point A does not equal to 0. If it does not equal to 0, an error will print. To conduct a parametric study, all we have to do is vary our value of theta. To do this, we are going to define a range for which we will sweep our angle theta. And we are going to define this as the variable angle swept, and it's going to go from 45 to 70 degrees in increments of 1. Next, we will pre-allocate our max compression and max tension arrays. Our max compression array is going to be a 0 vector with a length of angle swept. Our max tension array will be a 0 vector with a length of angle swept. Doing this decreases MATLAB's computation time. Next, we will sweep through our defined range. Before doing such, we will define our applied load, which is 40,000 newtons. To sweep through our defined range, we are going to raster the variable I from 1 to the length of angle swept. In doing such, we can call theta. Theta is angle swept, and theta is going to take a value of 45, 46, 47, all the way up to 70 each time we run through our for loop. Upon defining theta, we can define all our symbols and all our equations as we have previously defined. Next, we will define our equations in variables vectors, which allows us to create a solution structure. Our solution structure is based upon solving our equations for our variables. What we'll do at each unique value of I is determine our maximum compressive force, and we will do this by taking the max value of our solution structure. To determine our max tension, we will take the minimum value of our solution structure. In doing such, we'll have a max compression and max tension vector for which we can plot against theta. We will plot our max compressive force against theta, and we will denote this by a blue line, and we will plot our max tensile force against theta, and we will denote this as the red line. Plotting our compressive and tensile forces against theta gives us a very unique trend. At theta is equal to 45 degrees, our maximum compressive force, denoted as MCF, is greater than our maximum tensile force, denoted MTF, by a factor of 1.4. As we increase theta, both our maximum compressive force and maximum tensile force monotonically decrease, with our maximum compressive force decreasing much faster. Once we reach an angle where theta is equal to 60 degrees, our maximum compressive force and maximum tensile force are equal, and then for any angle greater than 60 degrees, our maximum compressive and maximum tensile forces take the same value.